Cool. Yeah. So, hi everyone. It's my pleasure to introduce Josh Russell. Josh is zooming in today from Providence, Rhode Island. He did his undergrad at the University of Missouri and got degrees in physics and mathematics. Then he went from the city of Columbia to Columbia University, where he did his master's and PhD. And at Columbia, he worked with Jim Garrity on really an impressive range of different topics, mostly using surface waves to invert for the evolution of oceanic lithosphere and different mantle dynamics. So not only is Josh a really exceptional seismologist, but he's also a really big contributor to the community as well. He has a bunch of publicly available software on his website for things like OBS relocation and waveform analysis and tomography. So definitely check it out if you're interested. And recently, after getting his PhD, he was awarded an NSF EAR postdoctoral fellowship, and that's led him to his current position at Brown University working with Colleen Dalton. So we're super excited to have Josh here for his virtual UTIG visit. And with that, I'm just gonna hand it over and let Josh tell you about his talk.
Awesome. Thanks, Brandon. Really appreciate having the chance to share some of our recent work with you guys today, focusing on trying to better understand the transition from continental rifting to seafloor spreading. And this work will be focusing on the eastern North American margin, and in particular on the lithospheric mantle and that signature that's sort of recorded from these processes that occurred much longer ago in time. So, okay, so yeah, I think it's kind of useful to just step back and take sort of a global picture before we really dive in. So of course, there are lots of interesting processes happening on Earth, ranging from subduction, which eventually lead to the origin of continents, and stable supercontinents, which eventually rift apart, and then eventually lead, if they're successful, will lead to passive margin or seafloor spreading and creation of passive margins. And then the cycle, of course, continues. For this talk, we're going to be focusing on this kind of portion of the diagram, and in particular, this sort of young passive margin regime. So right at the edge of when rifting has successfully occurred and the onset of kind of typical seafloor spreading has began. So for this, we'll look at the Eastern North American margin, or ENOM, which formed about 200 million years ago during the breakup of Pangaea. And it was sort of closely associated in time with the outpouring of camp magmas and flood basalts at around 201 million years ago. And in particular, this region has been very, very heavily studied in the past, which is really nice for giving us sort of extra context into what's going on here. And in particular, we're going to focus on this little boxed in red region, which is the ENOM community seismic experiment, which we'll talk a lot more about in a couple of slides. But this region consists of, this experiment consists of sort of multiple data sets that really allow us to look in more detail at this continent ocean transition than we've ever been able to before on this coast. And so part of this region, yeah, a couple of the very the useful sort of geophysical things that we can observe in this region stem from magnetic anomalies, and magnetic anomalies provide both information about structures that have been placed in the crust a long time ago, as well as some of the ages of these things. And so on the east, there are two in particular in the ENOM region that we'll focus on. One is the East Coast Magnetic Anomaly, or ECMA, which is a very strong positive anomaly that extends down most of the coastline here. And just east of that, or seaward of that, about 200 kilometers, is the Blake Spur magnetic anomaly, which is a little bit hard to see in this figure, but it's a much weaker magnetic anomaly. And sort of the interesting thing about these anomalies is that they occurred in a time where there weren't very strong magnetic lineations in the crust, recorded in the crust. So the timing of these two magnetic anomalies has been debated a lot in the literature. And so some of the more recent estimates have given the ECMA a timing of around 190 to 195 million years, and the Blake Spur magnetic anomaly of around 170 million years. But their tectonic significance and sort of which one is likely to mark the breakup of the full sort of continental breakup and transition to seafloor spreading is still being debated. So a lot of previous studies that have looked at the ENOM in particular have focused on the ECMA, which is that larger magnetic anomaly right near the coastline. And I think part of the reason is probably because it's such a prominent feature, and also it's much closer to the coastline, so it's a little bit easier to get to. So a lot of previous studies have sort of focused on that anomaly, and have sort of proposed that that is marking the edge of the continental shelf and sort of the continental lithosphere. And so anything east of that is considered kind of normal oceanic crust. However, there have been some recent work, in particular by Brandon, your very own Brandon Shook, as well as Anne Bissell, looking at the significance of the Blake Spur magnetic anomaly. So in particular, using data from that community seismic experiment, which extends much further offshore than data had previously. And the really interesting thing about their work is they found evidence from the crust in particular that instead of the ECMA being the transition to normal seafloor spreading, it might actually instead be the Blake Spur magnetic anomaly. And of course, this would then have implications for the timing of breakup in particular. One of the interesting things about this interpretation is that they've inferred a continental mantle lithosphere sort of west of the Blake Spur and in between, sort of the ECMA and BSMA. And so that's something that with surface waves, we'll be able to actually investigate a little bit further. There are some other pretty interesting observations across the Blake Spur, in particular in the crust, where the crust gets a bit thicker east of the Blake Spur. So the crust west in other words, the crust west of the Blake Spur is about 1 or 2 kilometers thinner than that to the east. There's also evidence for higher velocities in the lower crust west of the Blake Spur. And there's also another, you can't tell maybe that well from this figure, but the seafloor is much smoother east of the Blake Spur than it is to the west. And that might is likely to signify a change in spreading rate, where the spreading rate actually increased after formation of the Blake Spur. Okay, so again, we're using data from the community seismic experiment. So the 2 lines that I just showed you were these 2 margin perpendicular lines, line 1 to the north and line 2 to the south. There are also 2 margin parallel lines that are included, as well as an extension of these lines onshore. And that included both wide angle reflection refraction and multi-channel seismic reflection, and also broadband deployment of 28 seismometers, which is what I'll be using in this study. So just to kind of give you an idea of where these stations are relative to the magnetic anomalies, this kind of gives you a sense for that. The very most western part of our array is basically sitting on the ECMA. The Blake spur magnetic anomaly sort of extends kind of down the middle of the array, more or less. And then for reference, these lines 1 and 2 are shown. And they're going to be really important for our analysis because we're basically going to take Brandon Shook's VP model of line 1 and 2 and incorporate those directly into our modeling for the surface waves. And again, the question being sort of when did normal seafloor spreading occur? Can we tell this based on the shear velocity structure and also the seismic anisotropy? And in general, what can the seismic anisotropy tell us about mantle dynamics during the rifting? So just a quick primer on seismic anisotropy. So the upper mantle is made primarily of olivine, which is highly anisotropic, with wave speeds fastest along the A-axis or the 100 axis of olivine. And the really important thing that's been found in laboratory experiments is that when you shear an aggregate of olivine, the A-axes or the fast axes tend to align with the direction of shear or the direction of flow. So this is sort of just showing that from one of the original Zhang and Corrado experiments. And so that would tell us that if in the Earth, if we can observe seismic anisotropy and attribute it to the lattice preferred orientation of olivine, we can then back out a flow direction. So in the case of the oceanic mantle, we think of this in terms of at a spreading ridge, you have material coming up at the ridge, and then it sort of turns over due to corner flow, and then you have a shearing of material in the lithosphere in the direction of spreading. So and then that material would cool and sort of get fossilized in the lithosphere, and then that would be the signal that would be retained through time, and that would be what you would observe even much later in time. In the asthenosphere, it's tend to be thought of as showing present day flow. So that material is still being deformed. And in general, in the ocean, beneath the oceans, especially beneath the Pacific, it tends to align somewhat parallel to the plate motion direction. So that's sort of the typical observation beneath the oceans. So there was a previous shear wave splitting study at ENAM, and this is sort of showing the results of the anisotropy observed from shear wave splits. And so I won't go into detail about exactly how those are determined, but one of the sort of well-known issues with shear wave splitting is you don't have a sort of depth sensitivity to the waves. So the anisotropy that you're measuring could be anywhere from the core mantle boundary up to the surface of the Earth. Typically, it's interpreted that this is asthenospheric flow, and that's how it was interpreted for this study, that basically offshore, you have a margin parallel flow in present day, in the present day asthenosphere, which is an interesting result. And one of the things we want to get at with our study as well is to try and see how much of this signal might potentially be in the lithosphere. And in particular, is the lithosphere in this region anisotropic? And if so, what's the orientation of that anisotropy? So in order to do this, we're going to use surface waves. And then the nice thing about surface waves is that they have decent sensitivity to depth. So we can be pretty confident that all of the signal that we're observing is confined to the lithosphere and not contaminated by asthenospheric fabric. And for ambient noise, the idea is basically that you've got surface waves bouncing around in the oceans constantly, just due to interaction with the water wave with the seafloor. And if you sum over enough data over time, you can actually stack out the Rayleigh waves or the Green's function. And one of the issues we actually had while this is kind of an aside, I guess, but one of the issues we had with dealing with this data set was actually that there was a pretty strong amount of noise on the vertical channel, which we think is due to the Gulf Stream. You sort of drop your seismometer onto the seafloor and you hope that it lands pointing perfectly vertical, the vertical channel, but you can often get noise from the horizontal channels, and this really strong bottom current would produce a lot of noise on our instrument. So we were able to remove a lot of that using this tool called Attacker, Automated Tilt and Compliance Removal, by Helen Januszewski. It's a really useful tool if you're using this kind of data. I highly recommend it. And we were able to remove the tilt and quiet the stations quite a lot. And in particular, this is a really nice example because it shows this peak at around 15 seconds is the ambient noise signal that we care about. And so without doing that, it's really swamped by this tilt signal. So here are the Rayleigh waves that we observe. So these are sort of the raw waveforms on the left. And for each of these individual traces, it's representing a Rayleigh wave between two different stations in the array. And we can measure the dispersion. In the frequency domain, we use a Auke's zero crossing technique to sort of fit a Bessel function to these frequency domain spectra. And we can extract a dispersion curve for each station pair. So this is showing, here in the middle is showing the ray coverage at this particular frequency. So as I mentioned, we're using Brandon's VP model directly in our inversions. And this is really important for interpreting where the sensitivity of these Rayleigh waves as a function of frequency sort of map to in depth. And so we convert the VP to VS, assuming a VPVS of 1.8 in the crust and mantle, and a VPVS of 2.2 in the sediments, just based on, this is actually based on Brandon's line 3 model, which isn't shown here, but is the margin, one of the margin parallel models. And I'll talk about it in a little bit more detail later, but we actually have used both line 1 and line 2. But the way that we kind of extrapolate them across the array is by a constant depth contour. So basically, we take a point on line 1, for example, at a specific water depth, and we map that to all the other locations with that same water depth. And it does a pretty good job of kind of spreading that line out across the region. There's an implicit assumption that there's not a lot of along strike variability, but we actually do this with both the line 1 and the line 2 model, and our results don't change too much between them, and we actually use the average as our final model. So that's sort of our way around that, but I would be happy to talk about that more later if anybody would like. So this is just showing a shallow water sensitivity kernel for a Rayleigh wave for a range of frequencies versus a deep water station. And so these profiles on the left are basically from Brandon's model converted to VS. And there's some really interesting things that we can see that we sort of need to be careful about. One, if we look at the dispersion that's predicted from these two different models, so that's shown over on this little panel in orange and blue, you can see at the short periods, there's a huge difference between these two different models. And that difference is primarily due to the changes in water depth. So at the short periods in our data set, we're extremely sensitive to water depth. And you can actually see that in these sensitivity kernels as well. At the shorter periods, there's very different sensitivity to, for example, this 12-second wave here than there is to this 12-second wave at shallow water. So if you were to then take these shear velocity models and calculate dispersion, basically the synthetic phase velocity map for that model, here we're showing if you were to propagate shear waves through that model at 13 seconds period, you can see that the wave field is basically bending pretty badly and is sort of violating the assumption that we commonly make, which is that it's traveling along the Great Circle, which for much of this path, it definitely is not doing that. So we end up using these spectral element method calculations to estimate sort of a numerical sensitivity kernel that accounts for that ray bending. So here is showing the true path in sort of the solid line and the Great Circle path in the dashed line. And you can see they're quite different at this frequency. And so that's something we try to take into account. It turns out at, for example, 20 seconds period. So that was at 13 seconds. If you look at 20 seconds period, they're much closer together. The Great Circle path and the true path. So we don't have to worry too much. But if you want to look at azimuthal anisotropy at these shorter periods, you have to be very careful because the bias that you would find due to the off Great Circle propagation or the bending ray path would actually lead to an apparent azimuthal anisotropy. So this is showing the travel time of the Great Circle path versus divided by the travel time of the true path. And so you sort of get this azimuthal signal. So in order to avoid that, we actually don't solve for azimuthal anisotropy for periods less than 17 seconds, only periods greater, just to avoid this strong bias. So I'll talk about the anisotropy later on in the talk, but first I wanted to focus on the velocity structure and the phase velocity maps. So this is showing phase velocity maps from 13 to 32 seconds. And at the 13-second map, you can see that velocities decrease as you go away from the coastline. So here is the ECMA and the BSMA for reference in black. And that decrease away from the coastline is just because the water velocity is increasing. And you sort of see the opposite for 17 seconds up to 32 seconds, where velocities get faster as you go offshore. And that's due primarily to the thinner crust and potentially the faster mantle and more mantle sensitivity at those longer periods. So our inversion for VS, we basically take those phase velocity maps and invert them point by point for shear velocity as a function of depth. And we use a Monte Carlo style inversion to basically sample several different, to basically perturb the starting model we choose plus or minus 10% of the reference values from Brandon's model. And that allows us to get at the sensitivity of our results to the starting model. So we repeat this, we basically do 100 inversions for each grid point, and then take those ensembles as sort of the ensemble average as our preferred model, and then we can have an estimate of uncertainties as well. So the interesting thing with this inversion is that we find in the shallow mantle, we have much better sensitivity actually than we do in the crust. And that seems to be a result of just the sensitivity kernels in the crust being so sensitive to the starting model that if you perturb the starting model a little bit, you have to be pretty careful with how you damp things at the crust. And this is sort of highlighting why it is so important that we included the VP results in the crust. And we really wouldn't be able, I don't think we would be able to do this nearly as well if we didn't have those prior crustal constraints. So here are a few slices through the 3D model. The first A and B are showing crustal slices, and then C through F are mantle slices. And the one thing I wanted to point out for the mantle slices is that you can see a contrast in the velocities across the BSMA, even when we're just looking in these map slices, where velocities are typically slower west of the BSMA and faster as you go to the east. This kind of goes away as you go to deeper depths below 30 kilometers-ish. And in the crust, I don't have too much to say given that our sensitivity or our uncertainties are pretty large there. But I will point out we did have a little bit of trouble with the region of the model directly near the coastline, right at the shelf break, partly because the water depth changes so quickly there. And that was one of the sensitivities that I sort of showed earlier, that we have a really hard time recovering is that really sharp change in the water depth. And that's because we're using extremely smooth phase velocity maps. So this difference between the Blake Spur is highlighted if we look at cross sections along perpendicular to the margin. So here we've taken our 3D model and we're averaging over this red boxed region. And so it sort of represents an average margin perpendicular structure. And when we do that, we can pretty clearly see that there's a slower shallow mantle lithosphere west of the BSMA versus to the east. And we can look a little bit deeper to see what this means in terms of the actual quantitative values of velocity. And for this, we take averages over a boxed region west of the Blake Spur and a region east of the Blake Spur. And so these are those velocity models. And we can overlay on top of them some reference model values. So here, this light blue is for the no-melt experiment, which is a 70 million year old oceanic lithosphere from the Central Pacific. And in brown is a continental average velocity that is from Shannon Ritzwaller 2016. And so that's shown over here on the left. We've taken a region just onshore of our study region and just taken an average velocity profile for those points of the model, and that's shown in brown here. So it's much closer to what's observed west of the Blake Spur than east of the Blake Spur, and even the velocities that we observe on average are even a bit slower than this continental lithosphere. So the first hypothesis to explain these slower mantle velocities is just in keeping with the previous interpretation that there's continental mantle lithosphere underlying the crust, the oceanic crust west of the BSMA. And the idea being that you had melt sort of percolating through this lid, this thick sort of lid, forming oceanic crust on top. And then when that finally ruptured and broke, then you had sort of typical seafloor spreading producing typical oceanic mantle. Yeah, and so the key to this would be that the breakup then in this case would happen at around 170 million years old. Another hypothesis that we want to test is whether you can do this, whether you can produce a slow lithospheric layer by trapping gabbro into the cooling mantle lithosphere. So on the top is showing a sort of schematic for a fast spreading environment where you have melting occurring. You have very, very thin thermal lid and you have melting occurring essentially to the base of the crust. Down here below is showing a slower spreading case where you actually have time to cool and form a mantle lid, which would then sort of choke off some of these melt pathways, sort of shown in yellow here, that would then crystallize and be incorporated into the mantle. And this would be sort of slower gabbro material being mixed in with the ultramafic mantle. And this, this is kind of an important hypothesis to test because it would suggest that actually seafloor spreading did start at the East Coast magnetic anomaly and not later on at the Blake Spur magnetic anomaly. So the way that we've tried to test this is to basically add gabbro to these to the continental model until it matches the profile west of the Blake Spur, which is shown in orange here. And we've also taken our east of the Blake Spur profile and added gabbro to that in order for it to match what we observe west of the Blake Spur. And that's shown in blue. And so you can see we would need a lot of gabbro in the upper mantle for an oceanic setting in order to explain the velocities that we observe, and about half the amount for the continental case. And so we can then think about what would the equivalent amount of crust need to be to produce this amount, to allow this amount of gabbro to be put into the mantle. So the idea being that basically you're taking gabbro that would be in the crust and putting it into the mantle, resulting in a crustal thinning. And so this is just showing some results from Andesell's work, showing crustal thickness west of the BSMA versus east of the BSMA. And you can kind of see just generally from these profiles down here that the difference in crustal thickness across that region is about 1 to 2 kilometers. So if we then look at how much gabbro is required to explain the velocities, we can just integrate the area under these curves, and assuming that the crust is 100% gabbro, which is an assumption, would mean that in order for the oceanic mantle to explain, with gabbro inclusions to explain our observations, you would need about 3 to 4 kilometers of crustal thinning west of the BSMA relative to the east. And for the continental case, it's only about 1 kilometer, which matches pretty well with the observed crustal thickness values. So our interpretation here, then we can just sort of recycle Brandon's model for now. And our interpretation would be that in addition to the crust, these melts sort of percolating through this continental lid, forming the crust, some of them would be left over and sort of trapped and cooled into the continental lid. And these would be sort of preserved through time, as we see here. And this would then be in keeping with their interpretation that seafloor spreading initiated, normal seafloor spreading initiated at the Blake Spur magnetic anomaly. Okay, so that's sort of the story for the velocities, but we haven't yet talked about the seismic anisotropy, and I wanted to show the velocity structure first so we can sort of have that in mind when we think about the implications for the seismic anisotropy. So on the right here is showing sort of the raw data that goes into fitting the anisotropy, So each of these individual gray points is showing one dispersion curve measurement, so one interstation path, and we've plotted these relative to the mean as a function of azimuth. So you can see that that there's approximately a 2 theta pattern, and Rayleigh waves that are traveling in this sort of blue, aligning with this blue line, are traveling faster than waves traveling orthogonal to that. And it turns out that this aligns very well with the margin parallel direction. So we do observe margin parallel anisotropy, similar to what was observed in the shear wave splitting. However, our observations are sensitive to the lithosphere only, and theirs sort of integrate that sensitivity through the mantle. So that was just showing kind of the one-dimensional version of anisotropy, but we can also solve for a 2D map of variations in anisotropy across the region. And when we do that, we find that mostly the signal wants to be parallel to the margin. There might be a slight rotation sort of from west to east across the array. And if we look at the strength of anisotropy as a function of period, it's pretty consistent. It decreases slightly as a function of period, but I think the sort of striking, the more striking thing is the fact that the anisotropy fast direction is pretty consistently parallel to marginal to the margin. And so one conclusion of this is that some of the margin parallel signal that was observed from the shear wave splitting is likely attributed to the lithosphere, but we don't have from our data set, we don't know exactly how thick the lithosphere is. So, and we haven't inverted for anisotropy as a function of depth. So it's, we haven't done the calculation of whether all of the signal can be explained by the lithosphere, but I would hesitate to say that it could. But we could talk, yeah, we can speculate more about that later if someone wants to. So we can also, now that we know that the Blake spur is, Blake spur magnetic anomaly is kind of an important feature in our model, we can actually do an inversion where we allow there to be a really sharp break across that boundary. And when we do that, we still get an anisotropy direction that's significantly rotated from what you would expect, which is fossil spreading, and is much closer to the margin parallel direction. And this is kind of at odds with our this overall picture is sort of at odds with the general assumption for seafloor spreading, where fabric should actually be parallel, should actually be rotated 90 degrees from what we're observing here. And in particular, if the Blake spur represents a transition to normal seafloor spreading, you would actually expect that east of the Blake spur to have fossil spreading parallel fabric, which we don't observe. So to test this a little bit further, we can actually ask the question of, if we input a model with fossil spreading parallel fabric east of the Blake spur, can we then recover that using our data coverage? So it's basically testing whether it's just a data coverage issue versus a true signal. And so for our input model, it's 2% anisotropy everywhere with a 90-degree change in anisotropy across the Blake spur. And here I'm showing on the left is the recovered smooth model, and on the right is the recovered model where we allow there to be a break in the Blake spur. And just to sort of orient you on these plots, the black line is marking the input model, and then the yellow rectangle is the recovered value, and the colors in the background are showing anisotropy strength on the top panels and angular misfit on the bottom panel. So pretty much anything that isn't white signifies a misfit in the ability to recover those values. So although we have a pretty rough time recovering the exact amplitude, particularly for the smooth model, both models actually do a good job of recovering the direction of anisotropy. So this would suggest that if there really is a margin or a fossil spreading parallel signal east of the BSMA, we should be able to observe it, but we don't. So it's interesting to then compare this to a nearby study. So about 50 million years younger than the ENOM experiment was the FAME experiment. And this experiment also measured azimuthal anisotropy, but using PN waves in the upper mantle. And they observed anisotropy with the fast direction parallel to spreading rather than parallel to the margin. So there's a 90-degree difference in anisotropy at these two locations, but they're only separated in age by about 50 million years. So this presents kind of an interesting way to test a couple of hypotheses. One being that so one hypothesis is that you actually are recording the plate motion direction rather than the spreading direction. And one of the motivations for sort of looking at this are some of these global compilation data sets that show that as you, so here it's showing spreading rate on the y-axis, and then this delta alpha is the misfit of the lithospheric anisotropy relative to spreading. So a misfit of 0 would mean that it's parallel to spreading, so on. And you can see that as you, especially on sort of the average, as you go to slower and slower spreading rates, your misfit relative to the spreading direction becomes larger and larger, particularly once you get below about 6 centimeters per year. And the ENOM experiment was that region represents extremely slow spreading of about 0.6 to 1.3 centimeters per year, ranging. And if we look at the Atlantic only portion of this plot, you can see that it's extremely rotated from fossil spreading for much of the plate. So the hypothesis that we want to test is that because the spreading is so slow, the corner flow isn't able to actually align the olivine effectively in the direction of spreading, but rather the motion of the plate over the underlying asthenosphere instead is imparting the shear that's aligning olivine in the direction of plate motion. And so we want to test that using plate reconstruction models. So I'm showing here one plate reconstruction model that extends back to 200 million years in age. And on the top plot is showing the azimuth of plate motion relative to spreading. So an azimuth, so on this plot, a value of 0 would mean that plate motion is parallel to spreading. And we've kind of marked here in gray the orientation of anisotropy at ENOM, and then in tan, the anisotropy at FAME. And on the bottom plot is showing the velocity of plate motion, basically the velocity of absolute plate motion in solid compared to the spreading rate in the dashed line. And so for this particular case, you could see that for much of this time period from 160 million years to 200 million years, there's significant rotation from the fossil spreading direction. And then as you look to younger ages at the FAME experiment, the fossil spreading direction is almost, the plate motion direction is almost parallel to fossil spreading. And so it's sort of able to simultaneously kind of explain these two observations. However, this is becomes a little bit of an issue when you look at additional models. So this is now looking at 4 different plate reconstruction models. And they generally tend to show pretty similar behavior in the FAME timeframe, but are much more scattered at these older ages, in particular greater than about 160 million years in age. But even so, if you look at any one particular model, most of them are significantly rotated from the fossil spreading direction at these times, and then typically rotate towards something close to fossil spreading at younger times. So I don't think we can completely rule out this hypothesis that we had. There's also potential for additional contribution to the anisotropy due to, for example, these gabbro channels that we're sort of envisioning in that shallow lithospheric layer. So there's kind of a similar example to that would be shear wave splitting that was observed in the northern Ethiopian rift, where splitting tends to be parallel to the rift axis. And this was interpreted as either present day flow or melt, sort of aligned melt channels, or aligned cracks containing melt. And so we can sort of test that. On the right here I've shown, I'm not going to explicitly test it, but we can think about that. Here I'm showing the equivalent anisotropy as a function of depth that would likely result from favorably aligned gabbro channels, given the amount of gabbro that we think could be in the lithosphere, for both the continental and the oceanic cases. However, if we consider the fact that the anisotropy at the longer periods, greater than 25 seconds, for example, still show pretty strong azimuthal anisotropy that's parallel to the margin, it becomes difficult to reconcile that with the fact that where these measurements are most sensitive, there actually isn't much required gabbro. So it would be unlikely that this anisotropy produced only from the gabbros could explain all of the anisotropy that we're observing at these shorter periods. So it's possible that we actually have a combination of the two processes happening. And that's sort of our preferred model at the moment, is that you do have this continental lid that's about 15 to 20 kilometers thick. And within it are gabbro channels that might be aligned enough to produce somewhat of an anisotropic signal, but probably the larger signal would need to be some broader plate scale anisotropy. And in this case, we're envisioning that because the plate was so much faster, plate velocities were so much faster than the spreading rate at the time of the enom formation, that the olivine is actually recording the plate motion shear imparted onto the upper mantle, rather than what's typically assumed, which is the corner flow signal. And yeah, one of the things to just point out here at the very end is that this interpretation is consistent with the idea, the notion that seafloor spreading began at about typical seafloor spreading began at about 170 million years old, which has been previously proposed. And I will end there.
Awesome. Thanks, Josh. That was a great talk. Do we have any questions for him? Harm, go ahead.
Hi, great talk, Josh. So I was surprised to see that you have great control on the orientation of anisotropy in the enam area. You don't talk much about the magnitude of anisotropy, but you mentioned earlier in the introduction that in the shear wave splitting results, they give kind of null results near the coastline. And that is interesting. That would be interesting if that is true, in that you have a very strong parallel to the margin grain in the Appalachian terrains. And you see that now also between the ECMA and the DSMA. Are those two areas connected, or are they separate, do you think?
Yeah, that is a great point. Yeah, so I do have a figure showing that splitting just to keep everybody on the same page. Yeah, so Harm was showing, or was mentioning the fact that onshore, west of the margin, there are these mostly sort of northeast southwest splitting directions associated probably with the lithosphere, sort of sutures within the lithosphere. And then offshore, we observe a similar signal. And so I guess in my view, it feels like it would be difficult to, given that you've got this material sort of rifting apart, that it would be difficult to kind of retain that lithospheric suture fabric in such a coherent way across this sort of whole footprint that we're looking at. There's also I don't think I have a slide for it, but there are also some surface wave studies on land here, and at lithospheric depths, I'm thinking of Laura Wagner's, I think 2013 model. There's some pretty complicated anisotropy here in this region where the shore splitting shows nulls. So yeah, it feels like it's possible that this region of nulls could just be that the fabric is really complicated and is sort of a transitional region from this more regionally consistent stuff to the west to sort of the rifting and pulling apart signal to the east. So I don't know if that completely answers your question, but
yeah, I think you're saying they're separate, but
yeah,
they're two different regions. That's cool. Thank you.
yep.
Hey, Josh. This is Chen.
Hey, Chen.
Yeah. I have maybe two questions. Hopefully, just to be clear, I'm a petrologist. And I might ask you some, very sounds very silly seismology question. But here, my first question is: do you have a sense what is the kind of like a closure temperatures for the rheological features? Like the anisotropy feature you see here from seismological evidence. What is the temperature range you're talking about? Obviously, like you mentioned that in the asthenosphere, basically all the rheological feature probably will be erased, right? But you can only record the fossilized rheological features and anisotropies in the cold lithosphere. Do you have a sense like what is the maximum temperatures you can keep the rheological features?
Yeah, that's a great question, and I think an important thing to think about. So as far as like values on temperatures that you would sort of need to freeze in anisotropy, I don't know if I could give exact values, but people typically, I guess for the lithosphere, people are typically thinking about like something like an 1100 degrees C isotherm, but I don't think that we really have the I don't think we really have the
yeah. So I guess my kind of related question is if the temperature, let's say, is 800 or maybe 900 up to 1100. So once you have some other processes elevate the temperature, you can reset the lineation or the rheological feature, right?
Yeah. So you're saying if you were to reheat lithosphere, then you could kind of erase or reset that anisotropic signal.
Mm-hmm.
Yeah.
Yeah, because here you're starting from a rifting process, and you have a magma, like you showed here in the cartoon. When you have magma transfer through, obviously you could,
Yeah, I see what you're saying. So so the requirement that this shallow layer is anisotropic, I think is, I don't think that's an absolute requirement. So this continental layer could be isotropic, and we would still, if the material beneath it is sufficiently anisotropic, we would still observe the anisotropy of that underlying oceanic mantle. But there are ways to get at that by actually trying to invert your anisotropy data as a function of depth to see that, which we haven't done here. But I mean, if there was an LPO in this shallow continental lithosphere, I agree that it's possible that it could be reset if it's heat up enough. But But this alternative anisotropy that we're kind of envisioning here, what it is, I didn't actually talk about it, but it's sort of a shape preferred orientation style anisotropy rather than an olivine alignment, which is what would be happening deeper. So there are actually sort of two styles of anisotropy that would produce in a fast direction that's pretty comparable.
Mhm.
Yeah.
Cool. Yeah. I have another question. It's sort of related to your talk, and particularly for your title. Could you just briefly talk a little bit about, can you see the difference in terms of the anisotropies between active rifting and passive rifting margins, like when you?
Yeah, that's another great question. So, I mean, the passive, yeah, typically one type of anisotropy, so it's kind of related. In order to get to that question, I think you have to look at another type of anisotropy, which we haven't looked at here, which is radial anisotropy, which is basically the difference between waves traveling vertically versus waves traveling horizontally. And so for active upwelling sites, it's sort of expected that you would have a vertical fabric, which would produce a certain signature in radial anisotropy, whereas a passive upwelling, and not only that, but sort of return flow around the flanks, so sort of producing like a sort of vertical fabric even out away from the ridge. Whereas a passive upwelling, you just have material sort of passively going up and then turning the corner and spreading out horizontally. And so that would have a more horizontal radial anisotropic signal. Unfortunately, in order to actually solve for radial anisotropy, you need to use love waves. And the horizontal, and those are observed on the horizontal components of the seismometer, but we have some really noisy horizontal components, so we weren't able to look at love waves. But that's one way you could do it using anisotropy. I'm not sure that we can distinguish just with azimuthal anisotropy which which style is preferred.
Okay, thank you. Thank you very much.
All right, we are pretty much out of time for the talk for today. So thank you again, Josh, for coming and visiting and giving us this interesting talk. See you all next week.